Hello again. Today we will answer the advanced study assignment for experiment number 2. Resolution of matter into pure substance, paper chromatography. Just as a reminder, the advanced study assignment calculation are similar to the lab report calculation. In this particular case, question number 1 is the same calculations that are required for the lab report. Question number 1. A student chromatographed a mixture, and after developing the spots with a suitable reagent, he observes the following. So here's a picture of the chromatography paper that the student observed. The question asks for what are the RF values. So before we begin the question, first we're going to need a centimeter ruler. So you should obtain a centimeter ruler to answer this question. Second, let's define what is RF. RF is a fraction that's equal to the distance a sample moves divided by the distance a solvent moves. So basically, it's a fraction of how much movement occurred to the substance. So we need to know a few things. In order for us to know the distance the sample moved, we need to know where the sample was first applied. And then we need to notice how far it traveled. So if we look here, usually the point of application or the point where we spot mixtures are usually 1 centimeter away from the edge of the chromatography paper. In this picture here, it tells us already that this line right here is the point of application. So where this red dot is, this is most likely where the mixture was spotted. And this has a mixture of different substances, and we could see this by how far the mixtures separated from each other, because chromatography is a very good way to get mixtures to separate from each other according to solubility. So here is the first spot. The first spot does not seem to have moved very far. Versus the last spot right here, it moved much further. Well, what's the difference between this spot and this spot? Well, the solubility here is the difference. Chromatography separates substances according to their solubility. So this substance right here, did not move very far away from the point of application. That means it had a low solubility. Whereas this spot right here, or this substance, moved much further away because it has a higher solubility in the solvent that was used. So I need to know two distances. I need to know the distance the solvent moved. So here, this is where I stopped the solvent. And again, the solvent is usually also stopped 1 centimeter from it reaches the edge of the paper, because if we allow the solvent to travel further, then these substances will continue to travel, and the ones that are highly soluble may fall off the paper, and we will not be able to see them once we develop the chromatography. So this is why here it does not end all the way at the edge of the page, but the solvent stops right here, and where the solvent stops, we usually call that the solvent front. So that's why here it's labeled as the solvent front. So it's very easy to determine the denominator, the distance the solvent moves. We would get a ruler and we would measure from here to where the solvent front is. We will call this L. Actually in your lab manual, they have designated the distance for the sample moving to be D, and the distance for the solvent moves as L. So L would be from here to here. And if we get a ruler and measure it, this is about 8.05 centimeter. Okay, remember, whenever we use a centimeter ruler, okay, we have to use 2 decimal places. So this is 8.05 centimeter. Okay, and this would be from here to, it's really between, okay, it's between 8 and 8.1. Since it has not really reached 8.1, we're gonna estimate that it's halfway between, so that would be 8.05. Okay, next, okay, well, I have to identify which spot I'm gonna do. So here I actually have 5 spots, so I'm gonna start with the first spot, and the first spot, okay, is this one right here, and I'm gonna call this spot number 1, and I could just put a 1 as a subscript here, okay, and measure this one. But let's outline first our spots. Okay, this spot is very easy to identify, and when I come to measure it, I always measure from the center of the spot. So I'm gonna right there. Okay, I'm gonna leave this spot right here, the second spot, for later. I'm gonna do the third one. The third one is also easy. Okay, here is the third spot, and this would be the center of it. Okay, this here is a third spot, and I would measure it to the center. Okay, this spot right here, if you look at the dispersion of the spots, they look like 2 spots that are fused together. Okay, this here is 1 spot, and actually we're going to discuss why these spots, these 2 spots, did not separate like the others. And this is here another spot. So really we have 1, 2, 3, 4, and 5 spots. Okay, so we should have 5 different RF values. Okay, next I would get the ruler and I would measure from the point of application to the center of the first spot. So I'm going to go from here to here. Okay, if you bring your ruler and you've measured this, okay, you will find that this is exactly on the 1.6 line right there. If it's on the 1.6 line, we're going to have to use a 0 as an estimate. So this would be 1.60 centimeter. Okay. Now, notice one thing about the units. The units cancel. So that means my RF value is a unitless number. And if I enter this information into a calculator, let's bring a calculator here. Okay, so here I have 1.60 divide by 8.05. I get this very large number. Well, I cannot use the entire number, because if I look carefully, okay, at my, let's bring the calculator back on. If I look at my measurements, I have 3 significant figures on top in the numerator. This 0 here is significant because it's after a decimal. And 8.05 is also 3 significant figures. So because I'm dividing 3 significant figures by 3 significant figures, my answer has to also be 3 significant figures. So since I have 0.198776397515553, I have to stop at the third. So really, I stop at 0.198. And I look at the number next to it. If that number is 5 or greater, then I round up by 1. If it's less than 5, it's 4 or less, I keep the number the same. And since I have 0.1987, I have to round up to 1.99, and that will be my answer, 0.199, and it does not have a unit because the units, the centimeter units, have canceled, okay? So it becomes a unitless number, okay? And this is just a fraction of how far this first spot moved from the point of application, okay, in regards with the solvent, okay? Now what you have to do is do the same thing for the second substance, the third substance, the fourth, and the fifth. You should get 5 values, okay, similar to this. Of course, the RF value will increase as you go further up, okay, because here the substance moved much further away, so the RF value will be greater. The lowest RF value you could have is 0. So the lowest RF value is 0 centimeters, okay? Or I should say it's to be exact, 0.00 centimeter, because we should measure it. That means the spot did not move. That means it remained right here. There was no movement at all, okay? And the highest RF value that we can obtain will be 1.00, okay? And 1.00 means the substance is traveling with the solvent. That means when I stop the chromatography, the substance is there along with the solvent, okay? So that means the denominator and the numerator will equal to each other, so the highest value you could have is 1. The lowest value, where if the substance does not move at all, that means the numerator is 0, and 0 divided by any denominator will be 0. So that would be the lowest RF. Okay, now your job is to figure out what the other 4 RF values are, okay? And now we'll move on to question number 2. Question number 2. Explain in your own words why samples can often be separated into their components by chromatography. The answer is different substances have different solubilities in a given solvent, which allows them to be separated by chromatography. This is what we discussed in question number 1. Some substances, okay, are more soluble than others in the solvent that is used to run the chromatography. If the substance has a high solubility, okay, it will dissolve in the solvent and move with the solvent traveling further away from where it was spotted. That's the point of application. Okay? If the substance has a low solubility, it will not dissolve with the solvent and therefore will not travel far from where it was spotted. Very similar to the one that we answered in question number 1. That spot did not travel very far away from the point of application, therefore it had a very small RF value. The further away we move from the point of application means we have a higher solubility, our RF value will be greater. Question number 3. The solvent moves 3 centimeters in about 10 minutes. Why shouldn't the experiment be stopped at at that time instead of waiting 75 minutes for the solvent to move 10 centimeters? The answer is resolution improves as the distance solvent front moves increases. Bands are more likely to overlap if the front moves only a short distance. Okay, let me explain this a little further. Okay, let's assume, for example, the chromatography you had in question number 1 has 5 different mixtures, or it's a mixture of 5 different compounds. So once we start, okay, at time 0, so this here is at time 0 minutes, okay, all 5 compounds are at the point of application. When we wait maybe 10 minutes, the solvent starts to travel. So let's actually, okay, let's draw this. Okay, well, so this is the point of application. Okay. Okay, so after a little while, the solvent only travels up to here. So the substances, they start to move, but we can't tell, okay, which substance is what because they're overlapping each other. Okay, so it's very hard to distinguish which substance is which, and maybe this is after 10 minutes. Okay, if I wait a little longer, the solvent front, okay, will move a little bit higher. Okay, and now I'm gonna start to get a better separation. Okay, but they're not really fully separated yet, but I could see that they are, as the solvent is moving, the substances that are more soluble are traveling further away, and the ones that are not as soluble are staying behind. So this is maybe after 30 minutes. Okay, the longer that I wait, okay, the more resolution I get. Resolution here meaning that the substance that are in the mixture are separating much better. So if we wait till 75 minutes, then we reach the edge of the chromatography, and then we will start to see a much better resolve. Okay, and here of course I'm drawing, this is just a picture of what we might see. Okay, but we will see that the spots will start to separate and give a much better resolution, meaning that they separate from each other much better. But if we don't wait enough, it's going to be very hard to know which spot belongs to where each spot is, because it's just going to look basically as one big spot because everything is overlapping each other. So it will be very, very difficult to know if this is one spot, 2 spots, or 5 spots. Here we could start to get a feel that I have more spots, but the longer you wait, okay, the more resolution you will get, the better separation the substances will have, and they will separate much better from each other. And now we could start to measure the RF value, okay, from the center of the spot to the point of application. This part here, okay, will be your numerator, which your lab manual calls D. Okay, so that D will be from here to here. This is D. And then from here to where the distance that the solvent traveled will be your denominator, and we'll call that L. So d is the distance the substance moved, or the component moved, d, and the distance that the solvent moved, L, will be the denominator, and that will give you the RF value for all of your substances. Question number 4. In this experiment, it takes about 10 microliters of solution to produce a spot 1 centimeter in diameter. If the bismuth nitrate solution contains about 21 grams per liter, how many micrograms of bismuth ions are there in one spot? This type of question, sometimes you have to read a second time. And when you read it the second time, you have to ask yourself 2 questions. The first question is, what information is given to me in the problem? And the second question is, what information are they asking for? Okay, so I'm going to reread the problem again to myself, and I'm going to start to take notes of the information that's given and the information they're seeking. Okay, so it says, in this experiment, it takes about 10 microliters of solution to produce one spot that's 1 centimeter in diameter. So that's the first piece of information. I have 10 microliters of solution is equal to 1 spot. And if I need to know the diameter of that 1 spot, the diameter is 1 centimeter. Now, before we continue, I want you guys to be very careful with this Greek letter mu. Okay, I'm going to write here on the side. Students a lot of times write microliters as M, small m, capital L. That's actually milliliters. Okay, microliters, it's written as a Greek letter mu, capital L. That's micro liters. And do not use a capital M. Okay, units are case sensitive. Capital M is really mega liters. Okay, so we have to be very careful when we write units. Okay, so just please be aware of this. Okay, next. If the bismuth nitrate solution contains 21 grams of bismuth per liter, okay, well, that's a new piece of information. I'm given the concentration of this solution. The concentration is 21 grams of bismuth per liter of solution. Okay, next. How many micrograms of bismuth ions are there in one spot? So now that's, okay, so this here is information that's given. Now this is the information they're seeking, or this is the information they're asking for. They're asking for micrograms of bismuth in one spot. Well, here's the one spot. One spot is equal to 10 microliters. So really they're asking for how many micrograms, so I'm going to put a question mark, how many micrograms of bismuth are in one spot, which is really in 10 microliters. Well, in order to answer this question, we have a mixture of units here. Okay, they're giving us this question, okay, where they're giving us units in microliters and micrograms and grams and liters. Okay, in order to really answer it, we have to unify the units. But before we unify the units, what is the relationship between grams and micrograms, or between liters and microliters? So let's work out that relationship here on the side first before we continue. Okay, let's begin with grams. Okay, 1 gram is equal to a million, or 10 to the 6, or 1 times 10 to the 6 micrograms. It can also be written as 1 times 10 to the minus 6 grams is equal to 1 microgram. Okay, the rule here is you always, micro means a million, so here depending what you use, if it's 10 to the 6 or 10 to the minus 6, you have to keep one thing in mind. Big number goes with small unit, small number goes with the big unit, okay? So if we look on the top, I like to use the top options better, okay? If you look on the top, I have 1 gram equals 1,000,000 micrograms. Well, 1 is a smaller number than 1,000,000. So if 1 is small, it should go with the big unit, that's the gram, okay? And the million, because it's a big number, should go with the small unit, which is the micro, because they have to be equal. So small goes with big equals big goes with small, okay? And the same thing applies here, okay? Next, liter and microliter. Well, it's the same exact relationship, okay? 1 liter is equal to 1,000,000 microliters, or again, we could say 1 times 10 to the minus 6 liters is equal to 1 microliter, okay? So that's just the relationship that we will need to answer this question. Okay, so let's begin to answer the question. Okay, there are many ways to answer this. These are unit conversions in mathematics, so it's not one way only to answer it. So there are multiple ways to do it. If you do not use the same method that I use and you get the right answer, don't worry, as long as you understand the problem and how to do it. The way I'm going to answer it is I'm going to unify the units of the concentration to match the 10 microliters and the micrograms that they're asking for. Okay, so what that means is I'm going to convert 21 grams per liter, the concentration that's given, to micrograms per microliter concentration. Okay, so let's do that. So if I have, this is the information that's given, 21 grams of bismuth over a liter. I'm going to convert the numerator from grams to micrograms. I'm going to use this relationship here that we worked on the right hand side, and then later I'm going to convert the denominator, liters, to microliters, again using the information, okay, that we have here on the right hand side. Okay, now I don't want to change the concentration. Okay, I want the concentration to remain the same. So I'm going to multiply the concentration by a fraction that's equal to 1, because any number times 1 is itself. Okay, so here I'm going to multiply using a fraction that's equal to 1, but that fraction is going to allow me to convert the units. Okay, so I want to go from grams to micrograms. So what I really want is I want to put grams in opposite. So here the grams are in the numerator. I want to put grams in the denominator. And I want to put micrograms in the numerator. This way grams cancel. Well, what's the relationship? Well, here we see we have an equal sign. 1 gram is 1,000,000 micrograms. Okay, this fraction is equal to 1 because we said here they're equal. So, but what we just did, let me change the color, is we canceled the gram unit. So I no longer have gram, but now my numerator has microgram. Okay, I'm going to repeat the same thing for liters. Okay, so I'm going to do another unit conversion. Okay, so here it is. Now I have liters on the bottom in the denominator. I want liters on top so it can cancel. And I want microliters in the denominator on the bottom so it doesn't cancel. Again, this fraction has to equal to 1. So I'm going to look. 1 liter is equal to 1,000,000 microliter. So here is 1 liter is equal to 1,000,000 microliters. Okay, now let's go back to blue. Okay, if we look carefully, okay, liters Here is on the bottom, liter is on top, they cancel out. What are the units that remain? Well, here it is. Microgram per microliter. Okay? So let's erase this very quickly. Okay? Good. Now, I want you to notice one thing also. Okay? You see the number here? This is a million. This is also a million. So actually these numbers also cancel. Okay? So if you don't cancel them, you put them into the calculator, you're going to realize that, you know what? 21 grams per liter is the same as 21 micrograms per microliter. So now I converted my concentration from grams per liter to micrograms per liter. Okay, now what was the question? Well, the question now says how many micrograms of bismuth are there in one spot? Well, here is one spot. One spot is the same as having 10 microliters. Okay, so I have 10 microliters. Every microliter, according to my concentration, has 21 micrograms. So now I could calculate and I could say, and again, if you line up your units, you cannot go wrong. Okay, so I'm going to say 10 microliters of solution. That's my one spot. Okay, my concentration is 21 micrograms per microliters. Now notice, let me change the color again. Let me go back to red. Okay, notice here now microliters cancel. Okay, and what's the answer? Well, 10 times 21 will be 210 microliters. Okay, and that will be how much bismuth I have, because this is the concentration of bismuth in the solution. 21 micrograms of bismuth per microliter. So 10 microliters will have 210 micrograms of bismuth.